Okay, so what we're going to look at in 8.2 is we're going to look at a limit of a sequence, but we're going to look at limits of functions. So the idea, and I think this diagram, I hope this illustrates this pretty well to you. If you were to look at this, this is the sequence. So I've just got a picture of the graph of the sequence a to the n over n is n over n plus 1. And again, the sequence is just dots. We call that discrete. If you just have little pieces and it's not connected into a nice smooth function, that's just discrete items, okay? All right? I took a class one time called discrete math, and it's kind of talking more about not smooth continuous functions, but just discrete things, kind of like a sequence like that. But then the function, if you graphed on your graphing calculator x over x plus 1, all it's going to do is it's just going to connect those dots, because those numbers on the sequence are just particular elements of that function. They are points that are on that function. So the idea is what this is saying is if you have a function like this for all positive numbers, if the limit is equal to L of the function, then the limit of the sequence is also L, okay? Now that's a theorem that only works one way. Sometimes you have theorems that say if this, then that. It works that way, but the converse means you do that backwards. So what this would be saying is, this is basically just saying this. If we know the limit, and I'm just going to kind of write this in words. You don't have to write this down. I'm trying to show you what I'm thinking here. This is saying if the limit of the function is L, then, that's the kind of symbol for then we would say the limit of the sequence is also equal to L. It doesn't work the other way, okay? Now this is something they used in the book as an example. So for instance, if you had this sequence, if that was your sequence, and then that limit was that, now see, I'm doing this backwards now. So you can't say if the limit of the sequence is this, then the limit of the function is the same. It doesn't work that way. So the idea would be is if you worked with this sequence, and all this sequence is saying is, and this is an easy thing to do, it's just cosine 2 pi, cosine of 4 pi, cosine of 6 pi, and so forth. Now, do you guys see that that sequence always has the same value? Tell me that. What's the cosine of 2 pi? It's 1, right? Well, so is the cosine of 4 pi, 6 pi, 8 pi, and so forth, because it's the same point on the unit circle. So that limit is going to 1. But if you did it backwards, and if you did the limit of the function 2 pi x as x goes to infinity, that does not go to 1. Do you know why? Because what does a cosine do? It does this, right? It wobbles up and down. It doesn't converge to some point. It's always going to have a max, a min, so it's not going to converge to any point, although the sequence will. So the point on that is it's okay to do it this way. If you know the limit of the function is L, then the limit of the sequence is also L. That's a guarantee, but it doesn't work the other way. We call that the converse when you're taking a if-then statement backwards. So that's the idea. Okay, so with this one, on this particular example, what we'd say is the limit of the sequence is equal to the limit of n over n plus 1. That's what the sequence is. And then the limit of the function is x over x plus 1, like that. So the way this works is like this. The limit of the function, you can tell, is approaching 1 in my diagram, and my graph there like that. So that's the idea. Okay, in this case, the limit of the function is 1, therefore, so is the limit of the sequence. Does that make sense? Okay, so see, you're more familiar with doing limits of functions. So the idea is if we have a function that represents those values on the sequence, we can do that limit, then we can conclude the limit of the sequence is the same. That's the idea, okay? And then these are your basic limit laws. I'm just putting these on there for you to review. We'll be kind of doing those as we go through these limits. A lot of times breaking a limit of a sum up into sum of limits and so forth, and I'll kind of go over that as we do some of these problems. Okay, so what we're going to do now is we're getting more into the mathematical realm, not so much the graphical interpretation, but now more the analytic interpretation of this. So these are all sequences. So we're going to do the limit of the sequence. We're not doing series. This is sequences, okay? So what's happening on this is if you were to go through and write out the terms on this, and I'm just going to do this just two terms, just to give you the idea. You're doing 1/3 over 1 to the 4th plus 1. That's the first term in the sequence. The second term in the sequence is going to be 2 to the 3rd over 2 to the 4th plus 1 and so forth like that, okay? So if you do some of the arithmetic in your head, you're going to have 1/2, and then let's see, that's going to be 8 over 17 and so forth like that. Okay, so that's what appears to be happening when you're looking at that listing out the terms of the sequence. It's going like that. Okay, so what I'm going to have on this now, we're going to go ahead and we're going to do the limit as n goes to infinity of this sequence. Okay, like this. Okay, so we're going to do that limit and work that out like this. Now you can just kind of think of this as a function. So what we try to go ahead and do on this problem is we just try to think of, okay, if we just looked at, instead of n, we looked at x, and you don't actually have to do this. That would be like x to the 3rd over x to the 4th plus 1. Okay, like that. Now, from your background, you may already know what that is. I don't know. Do you know what it is?
0.
What?
0.
0, good. Okay, you may remember, you actually learned this a lot of times in college algebra. If you have a rational function, anytime the degree of the top is less than the degree of the bottom, then you have a horizontal asymptote that's 0. Okay, do you remember anything about that? That's nice to know, okay, because it kind of gives you the ability to do this real fast. The other thing that you could do on this, and I'm going to do it this way most of the time, and then we'll kind of get into L'Hopital's rule a little bit. You can divide by the highest power. Okay, so let's go through. This is a good thing that you want to make sure you know how to do, is the highest power of x is a 4th power. So we're going to divide everything by that highest power like that. Okay, that's what you generally try to do. Okay, if you do this now, you're going to have the limit, and then that numerator is going to be 1 over x. That denominator is going to be 1 plus 1 over x to the 4th, and then you're taking that limit as x goes to infinity. What I'm doing is I'm looking at the function, and if that converges, then the sequence is going to have the same value. So I'm using that theorem, okay? This one you can do in your head. You're really doing limit theorems. You're doing the limit of the top divided by the limit of the bottom. Okay, so just do it like this. What is the limit of 1 over x? Where's that going? 0. 1 over infinity. The bottom, you got a 1, and where's that going? I don't know why I put it. Yeah, that's right. So that's going to 0 like that. Okay, so what you would have is 0 over 1, so that would go to 0 like that. That would be the idea. Now, that problem right there, I'm okay if you saw that had a horizontal asymptote of 0, because if you do, then you just write the answer. That's fine. I don't care. Okay, yeah.
That's only true if it's difference by 1, right? So if it's x3 over x5 plus 1, it's not true, right?
No, it'd still be 0. It'd still be 0. What happens is in a rational function, no matter what the powers are, as long as this power in the top is less than that, then the horizontal asymptote is 0. Okay, it always goes that way. Okay, but if it's backwards, then it's a totally different situation. If it's backwards, then it has usually what's called an oblique asymptote. Okay, like slanted. Okay, if they're the same, like if you had like x to the 7th over x to the 7th plus 1, and you had that, then the horizontal asymptote's 2/3. Okay, so those are kind of the rules that you generally learn when you're dealing with that. Okay, let me show you one other thing on here too. So I want to show you also in this, okay, let's just kind of look at this way also, because I want to give you different kind of strategies you can do. So if you were doing the limit of this function, okay, if you plug infinity in, don't you have like infinity over infinity? Okay, so what does that mean you can do? You can L'Hopital it. Okay, all right. So we L'Hopital it. Okay, when you do that by L'Hopital's rule, you would have this. You would have 3x to the second over 4x to the third. Okay, like that. Well, you could L'Hopital again. It's still infinity over infinity, and eventually it would all go down to 0 anyway, if you did it that way. Okay, so you want to have different strategies, and you want to kind of use the strategy that's the most time efficient for you most of the time. Okay, like that. Okay, so that limit, we're dividing by the highest power. That's how that goes to 0. Do you guys understand that okay? This is all background Calc 1 stuff mostly. Okay, so you got to kind of review some of that stuff as we go. Okay, this one, what I'm going to do, this time I'm not going to worry about the function. I'm just going to leave the n alone, and we're going to do the limit as n goes to infinity of 3n to the third minus 1 over 2n to the third plus 1. I'm not even going to write the terms in that sequence out, because it doesn't matter. I know how to do that limit. Do you guys know what the answer to that limit is? Just boom, boom, like that. What is it? 3/2. Why is it 3/2? Right. The degree of the numerator and denominator are the same, so there's your answer. Those are called the leading coefficients. That's how that goes, okay? Your other strategy, and you don't need to write this down unless you feel like you need to, the other strategy, if you happen to not see that, is to divide everything by the highest power. Now, if you do that, that helps you see why this is the case anyway. So I just divide everything by 1 over n to the third. What happens is, that's a 3, right? Okay. This thing right here, that's really 1 over infinity. So what's that? 0. Okay, so that's 3 minus 0. The bottom, that's a 2. And then what is this? 0 again. Okay, like that. So there's your 3/2. Okay, so it works either way. But I want you to know that asymptote thing, because I want you to do some of these things fast. Okay, you don't want to forget that. Okay, does anybody have a question about what I'm doing then? So that would mean that these two sequences are going to converge to specific values. Okay. Okay, now I think the rest of what I'm going to do here today is do a L'Hopital's rule review. Okay, because a lot of times students forget some of this. Usually there's two cases that are pretty easy, and then there's a couple of cases that are a little bit more difficult to do. So you want to make sure you remember how to use L'Hopital's rule like you learn in Calc 1 generally. Okay, so first of all, what you're doing with L'Hopital's rule is you always have to make sure you have a certain form. And then you know what you do is if you have one of those forms, then you just do the derivative of the top and bottom and reevaluate the limit. Now there are times when you have to do L'Hopital's rule more than once, but as long as you have a form, that's what allows you to do the derivative of top and bottom. So one of the things that students do wrong all the time is they say, oh, there's a limit, I'm just going to do L'Hopital's rule. You only can do it when it applies. So first thing I want to kind of review is these two forms and what they mean. So if you're doing a limit, the first thing you'd want to do is just plug this number in. So let's see what we have. We have ln of e minus 1 over e minus e. Now a lot of times you can do this in your head, but you just have to know that it's a correct form, so therefore I can use L'Hopital's rule. What form is that? That's 0 over 0. ln of e is 1, right? So you got 1 minus 1 over 0, so you got 0 over 0. Okay, so that means, okay, L'Hopital's rule applies to the problem. Okay, so the way I usually do this is I usually just notate it like this. Equals by L'Hopital's rule. Okay, just kind of put a note to myself that I'm doing L'Hopital's rule. So what I'm going to do is I'm going to do the derivative of the top and the derivative of the bottom. So what's the derivative of ln x minus 1? 1 over x, right? 1 over x minus 0. So it's just 1 over x. Okay, so we have that. Okay, what's the derivative of x minus e? 1. Okay, so we got that. So what that's going to leave us then is we're going to have the limit as x approaches e of 1 over x. Okay, so now what do? You just plug the e in, right? Okay, so what you would get is 1 over e. Problem done. Okay, so what that means is if you looked at that function and graphed it on a calculator, it would just mean that as you're going to e, that limit is approaching 1 over e like that. That's the idea. Does that look familiar? Okay, all right. let's look at the next one. Okay, so let's plug in infinity. So again, you can do this in your head. You're doing e to the infinity over 3e to the infinity like this. Which form is this? That's an infinity over infinity. If you take e to an infinite power, you get an infinite number. The bottom's the same way. It's still infinity. Okay, like that. Okay, so that means that that is one of our forms. So what that's going to mean is we can do L'Hopital's rule. Okay, so we're going to go ahead and do that. You want to make sure you've got all your derivatives down pat and everything. Okay, so tell me what the derivative of e to the 3x is. 3e to the 3x, chain rule stuff. Okay, so that's going to give 3e to the 3x. Okay, what's denominator's derivative? Okay, you can do that in your head. It's 9e to the 3x. So it's really, if you want to write it down, it's like you have a constant, and then the derivative of e to the 3x is itself times 3, and of course the derivative of 5 is 0. And you can do this in your head. I'm fine with that. So you would have limit as x goes to infinity of 3e to the x, or 3x. Okay, and then that would be over 9 e to the 3x now. Okay, so what happens? Those cancel out. Okay, so it looks like you get the limit of 1/3. You can reduce that fraction down, so what's the answer? 1/3. Okay, the limit of a constant is always the constant. So that's the idea. Okay, now with this one right here, it's kind of built into the problem. I mean, see how you have a 1 there? And it's really, you can think of, even though the powers are not integers, you got to be kind of careful about that, but that's where that 1/3 comes from, is it's not that the degrees are the same, it's those powers are the same, like that. That's where that comes from. Okay, but you want to do L'Hopital's rule on that. Okay, those are usually the ones that students have very little trouble with. What do you think? 0 over 0, infinity over infinity, but there's more, and there's a lot more. We also have a 0 times infinity form and an infinity minus infinity form. There's a bunch of these forms, okay? So we're going to kind of review one of each of these and see what you remember on this. Now this time we're doing a right-hand limit, and so when we do this right-hand limit, let's just go ahead and plug in 0 and kind of see what happens, see which form we have. So we'd have like a cotangent of 0 minus 1 over 0, kind of like that. Okay, well, okay, what's happening on this? So first of all, if you take like this, sometimes students forget this, so I usually use the calculator to help you remember this. So if you take 1 divided by 0, that's obviously undefined, but what if you do 1 divided by something super duper close to 0? Then what do you get? You get something getting infinitely big, right? So this thing right here, that's going to infinity, okay? All right, it's not that it's equal to infinity, it's going to infinity. That's approaching infinity. Now we'd have to look at a cotangent. Well, one thing that helps a little bit is, and you don't need to put this graph there, I went ahead and put a graph to just kind of help you, remind you of this. So if you're doing a cotangent, this is what a cotangent graph looks like that you learned in a trig class. So as you are approaching 0 from the right-hand side, what's happening as you're going towards that asymptote? You're going to infinity also, right? So you have an infinity minus infinity form. So anytime that you're around an asymptote, like if you have a trig function or anything and you have a vertical asymptote, infinity is where it's going, either positive infinity or negative infinity, right? Okay, so we have that. Okay, so that means we have an infinity over infinity form. But what you have to do on this now is you don't just start taking a derivative. You have to write it as a fraction. This thing right here needs to be put together into a fraction before we can go through and do that limit. So what I'm going to do is I'm going to write this as the limit as x goes to 0 from the right-hand side. And what we can do on this is, what is a useful trig identity for a cotangent? It might come in handy. Cosine over sine. Good. Let's give it a whirl and see what happens. Okay, so we have cosine x over sine x like that. And then we have minus 1 over x kind of like that. Now we need to get a common denominator, because we have to have a we got to do L'Hopital's rule of the top and the bottom. So we're going to get a common denominator, and we're going to put that whole thing together. Okay? So if we do that, we're going to have limit x goes to 0 from the right-hand side. Common denominator is x sine x. So I'm just going to take this, and I'm going to multiply this by x over x. Like that. Okay? And I'm going to do this, and you can do this in your head if you know what you're doing. 1 over x, and then this one I'm going to multiply by sine x over sine x like that. That way I'll have this in one fraction. So you got to work with this before you even do L'Hopital's rule. So that's going to give me the limit as x goes to 0 from the right of x cosine x minus sine x all over x sine x like that. Okay, so we got that. Okay, so now what's going to happen on this is we're now ready to go ahead and do L'Hopital's rule from here. Because what's happening here, and before we do this, I want to show you one thing on this, is if you plugged in 0, okay, and you don't need to write this down, just pay attention to this. If you did 0 times cosine of 0 minus sine of 0 over 0 times sine of 0, do you know what form you would have now? You have 0 over 0. That's remember, when you have a fraction, you can either have 0 over 0 or infinity over infinity. So we do have a 0 over 0 form, right? If you do the arithmetic with that, that's what you have. So that does mean that now we can do L'Hopital's rule, but only now, okay? So now we're ready to do that. Okay, so we're going to do the derivatives and kind of see what we get. This one gets a little messy. So we're going to have limit as x goes to 0 from the right-hand side. So I'm going to go ahead and do the derivative of the top. So I'm going to do L'Hopital's rule. Okay, this piece right here is a product rule, and that piece is a product rule. Okay, so if we do the derivative of this, that's going to be first times derivative of second plus second times derivative of first. So derivative of cosine's negative sine. So that'll give you that. And then we want to do the derivative of sine x. So that's a cosine x. So that's just minus cosine x like that. And then the bottom is going to be another product rule. Okay? So if we do this, we're going to have first x times derivative of second cosine x, then do it backwards, plus second sine x times derivative of first. Okay, everybody with me on that? Okay. All right, now what we need to do with this is we need to clean it up and then see what we have. Okay, we may still have a lot of work to do on this one, I don't know. Okay, so I'm going to go ahead and let's see kind of what we have here on this one. So it looks like if we went through and plugged a 0 in now, we'd still have a 0 over 0, I think. That's what it looks like. So I'm going to clean this up here, and let's write this as negative x sine x cosine x. That's just putting that stuff together, minus cosine x all over x cosine x plus sine x like that.
Don't we need to have it actually plus cosine x instead of the cosine x's would just cancel that, so it would just be negative x over sine x.
What's up? What cosines?
See, you have x sine x, but then instead of adding cosine x times 1, you just multiplied the first term together. See up here. Up here.
Point it out, because I'm not seeing it.
Up here. It would be negative x sine x plus cosine x minus cosine x.
Oh, plus. Thank you. I didn't see the plus. Okay, thank you very much. Okay, that's important. Let me try again. Okay, yeah, so we'd have negative x sine x, okay, plus cosine x. Yeah, then the cosines will cancel. I'm so glad you caught that, because then I would be doing L'Hopital's rule again and going through all that mess again, okay? All right, so everybody with me then? Does that look good? Okay, yeah, so the cosines cross out. So then you would have the limit as x goes to 0 from the right of negative x sine x over x cosine x plus sine x. Okay, well, unfortunately, it looks like we still have a 0 over 0 limit. Okay, we do, because sine of 0 is 0, or an x is 0. That whole numerator is 0. so is the denominator. Okay, so what do? We L'Hopital it again, okay? So hopefully we only have to do this 2 times. So let's do L'Hopital one more time and see where this leads us then, okay? All right, so let's see. This is a product rule. So when we do this derivative, you got a couple of product rules going on again. You got a product rule there. You got a product rule there. Okay, so we're going to go ahead and do that. So this is going to be first. I'm just going to use negative x as the first. Derivative of second is cosine x. Okay, plus the second, which is sine x. Derivative of negative x is -1, so that would be what your product rule gives you there. Okay, go to the bottom, product rule here, so first is x, derivative of cosine is negative sine, plus second, cosine x, derivative of x is 1, and plus sine x like that. Okay, so we got that. A couple of product rules on there. And then we're going to have to just see what we have and see if we're ready to do a limit now. What's that?
You put a plus sine x instead of a plus cosine x on the bottom for the last term.
First derivative second, second derivative first, sine x.
But then you put sine x.
Does somebody need to point this out to me again? What am I missing here?
The last plus sign. Most recent line.
Jeez.
Sine x. And then you just took it over and you just put another sine x. But it should be cosine x.
Oh, okay. Jeez, man. I said this, I'm going fast. That's what's happening.
No worries.
Okay. It's just because, Calc 2, you do product rule a lot, so I'm kind of getting to go a little fast. So yeah, thank you. That is plus cosine x. Okay, now am I good?
Yeah.
All right, very good. Thank you. Okay, so let's see what we have now. So we have, looks like, limit x goes to 0 from the right-hand side. I got negative x cosine x minus sine x. And then the bottom, don't really see any like, well, I got like terms there. So you could have negative x sine x and plus 2 cosine x like that. Okay? Now, let's see if we've got a 0 over 0 thing again. I think we're good now.
Yeah.
We are, thank goodness. I hate L'Hopital more than 2 times. Okay. Sometimes L'Hopital's rule is just what you have to do. So now if we plug everything in, we're going to have negative 0 cosine 0 plus or minus sine 0 all over negative 0 sine 0 plus 2 cosine 0. You can do a lot of this in your head. Just be careful when you do that. So what you would have then is you'll have really 0, cosine of 0 is 1. Sine of 0 is 0. And then the denominator you have 0 times 0. Again, sine of 0 is 1. And then cosine is 1. And that's what saves us, is that right there. So what we have is 0 over 2. So 0 is the answer. Okay, how about that? Okay. That's not fun to do all those derivatives, but sometimes you get into that situation where you have to do that a little bit. So that would be an idea of how you would have to do an infinity minus infinity. And the important part of that is that you need to make sure you understand is you have to verify that it's infinity over infinity. That's step 1. After you do that, then you must get that into a fraction, verify that that's 0 over 0, then do L'Hopital's rule. You can't miss those steps because you don't want to do L'Hopital's rule when it's not applicable. Okay? Okay, so let's do, this next one's not too hard. This one doesn't have a lot of steps in it, so let's do this example of x cosecant of x. And then I want to finish up with doing one other thing. I want to do 2 more examples, and then that'll be good enough for today, I think. So, okay, so let's look at limit x goes to 0 of x cosecant x. Step 1 is figure out what you have. Okay, if you plug in a 0 there, and then plug in a 0 there, we need to figure out what form that is. So one of the things I went ahead and put, this is not on your handout, but I just put a cosecant graph to help you remember, because cosecants have asymptotes, right? And what happens is, if you look at this, the cosecant of 0 is really 1 over the sine of 0, right? but the sine of 0 is 0. You're undefined, therefore you have an asymptote. So if you looked at this, this is a graph of a cosecant. So if you traced along this, as you're going to 0, where's the graph going? It's going to infinity, right? So again, you're closing in on an asymptote, so you're going to infinity. So that means that what we have is we have 0 times infinity. That's what the general form of that is then. Okay, everybody with me on that? See, these trig graphs, they're just going to come up from time to time. You need them when you're dealing with limits and other things. So you want to remember how that goes. So now let's look at what we would do. So the way that you would want to do with this is you probably have a useful trig identity. What do you suggest I do as my next step? 1 over sine, exactly. Okay, just go ahead and put it as limit x goes to 0 of x over sine x. Okay, now plug in a 0. If you plug in a 0, what form do you have? 0 over 0. So what does that mean? You are allowed now to do L'Hopital's rule. Okay, I'm really emphasizing that you need to know when you can use L'Hopital's rule. That's super important. Okay, I think this one's easy. Okay, so by L'Hopital's rule, you would have the limit as x goes to 0. Okay, and I think I meant for this to be a right-hand limit. It doesn't really matter, though, because if you're going to an asymptote, you're either going to infinity or negative infinity. That doesn't make any difference. So the derivative of x is 1. Derivative of sine is cosine of x. Plug it in, and then we're done. Okay, so this one's easy. That's 1 over cosine of 0. So that's 1 over 1. Therefore, the value of that limit's going to be 1. Okay? Calc 1 problem. Classic Calc 1 problem. Does that look okay to everybody? Okay? And we're going to do this lots of times when we're dealing with sequences and series. Okay, let me do one more example. This is the one that students don't like. I love it, though. Okay, so what this is we've got these 3 forms. I'm just going to do one of these. You have 1 to infinity, 0 to the 0, and 0 to the infinity to the 0. You have an exponent. That's the key. If you have an exponent, you think logarithm. It has something to do with a logarithm. So the way that I tell students to do this is, first of all, if you plugged this in, this is a real interesting problem, too, to think about. You would have 0 to the 0, right? So that's the indeterminate form. So anytime you have one of these forms, this is the way I teach this. Our textbook does this slightly different. They don't show all these steps, but I think it's important to do it this way. Just go ahead and write down y equals x to the x. And then we're going to do the logarithm of both sides. And that kind of helps you a little bit. Okay, so what I'm going to do is ln of y equals ln of x to the x. Okay, now what do? Bring the x down. Logarithm property. So we have ln of y equals x times ln of x, like that. Okay? So what I'm going to do now is I'm going to put this limit together. And if you don't write your steps this way, there's a tendency to forget stuff. So what I'm going to do is I'm going to have you write this as ln y is equal to the limit as x goes to infinity from the right-hand side of x, ln of x, like that. Okay? So see, all I've done is I've changed that. I'm just saying y is equal to this. And then at the very end, I have to solve for y, okay, to get the value of that limit. Does that make sense so far? Okay. Now, let's look at what we have here. So one thing that you have here is when you look at this particular limit here, that's going to 0 right there. So that's going to 0. Now, what is the ln of 0? That's an interesting question. It's undefined, but if you look at an ln graph, an ln graph looks like this. So where's it really going? Negative infinity. But it doesn't matter if it's plus or minus infinity. All we care about is it's really a 0 times infinity form. That's what it is. Okay? So that means L'Hopital's rule is going to apply to this. But the first thing we got to do on this is we can't use L'Hopital's rule until we write this in a fraction. So this is the next thing that you have to think about. And this is another place where you might get stuck from time to time. Sometimes I get stuck on this, but if I remember that I got to have a fraction, then that leads me to this next step. So what I'm going to have you do is write this as ln x all over 1 over x. And I'll pause there and see if you understand what I just did.
Yep.
Is that the same? What happens if you divide by 1 over x? What are you really doing? You're multiplying by x. I changed it in a fraction. That's kind of a clever way of doing that, but now I'm ready to do L'Hopital's rule. Okay? Because what I really have on this now, if you think about this now, if I have ln of 0, that's going to infinity. Okay? Or negative infinity, really. And if you do 1 over 0, that's going to infinity. So it's an infinity over infinity form. You see what I'm talking about? Okay? ln of x has an asymptote at 0. 1 over x is going towards infinity. So now I can use L'Hopital's rule when I do this then. So I'm only doing L'Hopital's rule on the right side. That doesn't have anything to do with that. That just keeps coming down. So we're going to go ahead and do L'Hopital's rule now and see what we get. So that's going to be the limit x goes to 0 from the right-hand side. Okay, now it's easy. What's the derivative of ln x? 1 over x. Okay, now we still have to do the derivative of 1 over x. So write that as x to the negative 1. So that's going to be negative 1x to the negative 2. So that's negative 1 over x squared. So you got that. Okay? Does that make sense? Okay. Bring the ln y down. Don't forget about that. So now what you have is you have 1 over x divided by negative 1 over x squared. So that's 1 over x times negative x squared over 1. So that looks like that is just negative x. Okay? So what we have is the limit x goes to 0 from the right of negative x. Okay, and that's algebra. I'm doing the algebra kind of quickly over at the side of my paper. Everybody following along okay? Okay, so I'm almost done. Now we can do this limit right here. I mean, the graph of, what is the graph of negative x? That's a line, right? Linear function, plug the 0 in. So if you plug a 0 in there, you just get negative 0 or 0, right? So you end up with ln of y is equal to 0. Now the limit is not 0. That's one of the things students make mistakes on. This is really a base e, isn't it? So what do you say? Exponential form, then ultimately you have what y is. So you would have e to the 0 equals y. So the value of that limit's 1. Okay, a lot of work on that, but you would conclude that the limit x goes to 0 from the right of x to the x is equal to 1, like that. Okay? And here is a graph. I just did this on the graphing calculator. If you put x to the x in, this is what the graph looks like when x is greater than 0. Okay? And it does go, you can tell it goes to 1 like that. Now, if you want something to really think about, to wrap your mind around this, is actually very interesting, at least it is to me. If you look at x to the x when x is negative, it gets crazy. Because you would have numbers like negative 1 to the negative 1. Negative 2 to the negative 2, negative 3 to the negative 3, negative 2.5 to the negative 2.5. It gets really interesting. In fact, it jumps around chaotically because sometimes you have negative answers, sometimes you have positive. That's a good one to wrap your head around, okay, if you're bored on spring break. Okay, don't have anything to do. Think about x to the x on the left-hand side. That's a good one, okay? All right, well, have a great spring break. Don't forget to study and do homework. And when you get back,